Hey, we're live.
Welcome. Welcome, everybody. We'll get started in just one second. We are excited to just wait for a second while everybody joins. All right. Thank you, everybody, for being here. We're excited to share with you today. My name is AJ Steers, and today we're going to be talking about building data-driven chat applications with Airbyte and Pinecone. With me today, we have Joe and Rowie, Joe from Airbyte and Rowie from Pinecone. We have a nice, Joe will be giving a walkthrough of how to build a chat-based data application. And Rowie will be talking about Pinecone and vector stores and how to get data into vector stores, what is a vector store, and how to work with those. A quick introduction to Airbyte. If you're new to Airbyte, Airbyte allows you to move data from any source to any destination. We have over 300 quality connectors, open source connectors able to be interchanged, so any source with any destination. And we offer great pricing and open source and self-managed and hosted options. And Airbyte is, we have CLI options, we have a Terraform deployment option, and you can schedule all of your jobs to, excuse me, to execute whenever you need them to run, or you can control them via API. All right, so that's a quick intro to our flow, and I'll hand it off to Rowie to talk about Pinecone.
Thanks, AJ. So welcome, everybody. In this short 10-minute kind of preview of Pinecone, I'll give you a little bit of an intro into what kind of motivates us to use the vector database in the first place. I'll talk about what vector embeddings are, then we'll dive into what a vector database is, and then I'll present a couple of architectures, one for general application architecture that uses a vector database, and then a specific set of slides that will talk about retrieval augmented generation, or RAG, and we'll talk about that a little bit more throughout this presentation. So here's a quick intro. Let's talk about how AI, quote unquote, thinks. Obviously, it doesn't think like a human being. There are a lot of corollaries, but substantial differences. We can say that AI sort of mimics the way that the human brain works using neural networks. These neural networks are basically interconnected layers of artificial neurons. And these networks learn to do all sorts of interesting things by being exposed to very big amounts of data that basically adjust the connections between these layers of neurons. And then once these neural networks are trained, they're able to basically extract high-level features, what we call vector embeddings, from the data, and then they're able to extract high-level features and make decisions or predictions. And the internal representation of this data is what we know as vector embeddings. So let's talk about a little bit about what vector embeddings are. Embeddings are essentially just numerical representations that capture some relationship between discrete objects like sentences or paragraphs or images. And they represent these relationships in a continuous vector space. And that means that we basically are able to take that information that exists, for example, in semantic space, and project it into a numerical space or vector space, and still maintain the underlying relationship between those things. If we were to visualize these embeddings, right, we'd have to use something very simplified, because embeddings are usually high dimensional, meaning they have more than just 3 dimensions. But in this illustration, we can see an example that kind of like gives us an intuition about how these things work. So if I took, for example, a set of words that have some semantic correlation between them, what we would see in the embedding space is that these concepts and their corresponding embeddings are located in some proximity to one another within this embedding space. So here we have, for example, the days of the week, and we see those as being clumped together in a cluster. And we see that there are other embeddings that are essentially unrelated to those concepts, and those are farther away from these from this set of concepts. So embeddings basically don't draw on just like the value of a particular surface form, a particular word, but rather from the context in which they reside. And again, we're talking about a semantic use case. So for example, we have here 3 sentences that use the word bank, and each one of them is going to be represented differently within the embedding space. So where's the Bank of England, where's the grassy bank, and how does a plain bank, all have completely different meaning. And so the word bank, even though it's the same surface form, is going to be represented as being farther apart from the other 2 in the embedding space. And then conversely, if we have 2 sentences that have completely different surface forms, but still encapsulate the same semantic meaning, those are going to be represented close to one another in the embedding space. Okay, so now we have some sort of an intuition about what vector embeddings are, what is a vector database, and why do we need it? So like other data types, when we work with embeddings, we want to use the right tool for the job. So when we store key values, we would probably want to use a key value store. When we store documents, we probably want to use a document store. When we store nodes and edges, we probably want to use a graph store. And when we store embeddings, excuse me, and specifically any kind of vector, we would want to use a database that has been created specifically for that purpose, because the way that you traverse, index, and retrieve and upsert these vectors is going to come with its own unique set of challenges, and so we want to use a database that has been optimized and built for that particular purpose. So, what does a vector database do? A vector database allows us to manage these embeddings at scale. So, unlike a vector index, which allows us to save these embeddings and query them on our in memory, right, within our machine, a vector database persists those vector embeddings and then applies all sorts of algorithms to optimize the way that we both query those embeddings and then and potentially change them, update them, delete them, etc. It also knows how to efficiently again query and provide and retrieve similar vectors given a query vector. And it uses that based on some similarity metric that we can choose when we set up our index. And perhaps most importantly and most usefully, it allows us to associate a layer of metadata with the vectors that we are storing. And it will become evident why this is helpful when we talk about RAG a little bit more. So let's talk about Pinecone a little bit. So Pinecone is a fully managed vector search engine, a fully managed vector database. It basically allows, again, like I said, for a very efficient vector search with very low latency. It is a distributed database, and so it is essentially infinitely scalable. It provides the best ways to interact with the database, which make it a lot easier to, again, do all these operations that I've talked about, querying, upserting, deleting, etc., without having to manage all the overhead that's required to maintain latency and performance. And of course, like I said, it's managed. And so you don't have to worry about, again, all the overhead that's required to set it up, to scale it, to make sure that it's secure and compliant with standards like SOC 2 and HIPAA, etc. And of course, it provides all the bells and whistles that you would expect from a database, like observability and billing management and all that. Okay. Now that we've talked about Pinecone, let's look at what an application looks like that actually uses a vector database. So in most cases, you would see a sort of a dual flow kind of architecture, where we start with a certain set of content that gets embedded, and then that embedded content gets associated. Each embedding gets associated with some set of metadata, and that metadata is then upserted using the API into the vector database. And then the second leg of the journey is the application, where the application has some query coming from a user. That query gets embedded as well. We query that, we take that embedding for that query, we query the database, and we get the results back with the metadata associated with that query result. So let's talk about RAG a little bit. RAG has been really the talk of the town for the last 2 or 3 or 4 months, and that's because of its its ability to make LLMs incredibly useful and hallucinate less. But let's talk about that a little bit. So again, generative AI has been all the rage. It's capable of doing really impressive things, from generating music to generating pictures to generating text. But it definitely has some limitations. The biggest one of which is that any LLM, any foundation model, is limited to the data set that it was trained on. And so it would be able to retrieve, it would be able to generate responses only based on that initial data set. And that means that when we're interacting with it, and if we ask it questions that it may not have concrete information about, it will still try to generate a response, but that response might be incorrect, or completely false, completely invented. We call these hallucinations. That's been a well-known problem with LLMs, and that's kind of what vector databases are here to solve. So vector databases can mitigate, not eliminate, but mitigate this problem to some degree by providing sort of an anchor to the real world, where we take data that we know, that we trust, that we can basically say is correct, and basically build a bridge between the user query and the LLM. And the way that that this is done is by taking all of this trusted data that we have, embedding that trusted data, inserting it to the vector database, and then when the user queries the LLM, we take the user's query, we embed it, we query the vector database. The vector base responds with similar, with semantically relevant content. That's usually, again, it's both embedded and stored in the metadata, or some reference to it is stored in the metadata. And then we can take that semantically relevant content and inject it into the context window of the LLM, such that the response of the LLM is going to be based on that content and not other content. And in that way, with some clever prompt engineering, we can reduce the amount of hallucinations that we get from our LLM. So let's look at a typical architecture for a RAG application. For example, if we have a data set that lives on the web, we take a set of URLs that we trust, we crawl those URLs, we chunk the data that comes back from those URLs. In some cases, we transform the actual HTML into a content type that is more. Sorry, did we lose the? Oh no, sorry. We transform that content type into something that is a little bit more easy for chunkers to deal with. For example, Markdown. Once we have chunked documents, we embed those documents and again upsert them into the database with some corresponding metadata that's going to help us when we retrieve that content. And then on the other side, we have the application. The application makes a query. We take the query, we embed it. We use a metadata filter to basically limit the search that we're performing on the vector database, and then we retrieve back results. We stuff them in the context window, and then that context goes back to the LLM, and then the LLM can stream back its response to the application. And with that, I think that is my last slide. So I will hand it off to Joe.
Thanks. So the place where Airbyte can, in the end of the whole flow Roy just presented, Airbyte's place is the ingestion phase. So we've seen that you need to extract the data from the original source, then you need to process it in some ways, which involves splitting it up into multiple chunks if an original blob of data is too large, embedding these and then storing the text, the embedding vectors, and metadata you need within your application in the vector database. And Airbyte is encapsulating this flow. So when we are zooming into this section, then this is how things work when using Airbyte. There's some source of data. In this case, I just took the GitHub API as an example. In GitHub, there's lots of data stored that might be relevant for language models, for example, issue descriptions and PRs and this kind of stuff. So what Airbyte is doing is, in Airbyte, there's two parts. There's the source and the destination. In this case, Airbyte would be the source, Pinecone would be the destination. The GitHub source contains the logic to query the REST API and extract all data from there. In this case, we're just interested in the issues. Data will flow in form of records, which are individual units of data. In this case, one record maps to one issue with all the fields that the GitHub REST API gives to us. And these records will be streamed to the destination. The source implementation itself is configured in two ways. There's the configuration, which is things like which repo should I read the issues from, and what's the early start date I'm interested in issues. And then there's the state part, which is relevant when doing more than one sync, more than one replication from source to destination to only update things that changed since the last time things got replicated, but we'll get into this later on. So when the issues get emitted from the source and get forwarded to the destination, then a relatively similar thing happens there. The destination has a configuration as well. In this case, this is the credentials and the location of the Pinecone database, and also how to the credentials for running the embedding. And this destination is not just moving the data into the destination, the database, which is what would happen, for example, for a warehouse, but it's doing all of these steps the RAG ingestion flow contains. So it is processing the data in terms of extracting text and metadata and having them separately. Then it's doing the chunking into individual text chunks. Then it's embedding these text chunks, in most cases by sending them to an external provider like OpenAI to retrieve the embedding vectors. And then it's eventually loading the text and the metadata and the vectors into the Pinecone database where we can build an application on top of it. So to illustrate how this works, I'm going to do a demo here. And the demo I will show you is a connector development bot. You can probably imagine that when building a tool like Airbyte, there's a huge amount of sources we want to support. And a lot of them are relatively similar to each other, right? A lot of them are REST APIs, and they contain things like pagination, and you need to plug the records out of a nested JSON structure that comes back as a response for the HTTP request and this kind of things. And authentication is either using basic auth or it's using a bearer token or auth. There's a limited amount of things, and we encapsulated all of them and made them really easy to use behind an API, behind the UI called the connector builder. But of course, there's still a bunch of complexity into this, and it's not always easy to know how to solve a specific case. So what this chat application is about answering questions about the connector builder. And to do this, of course, we need to feed the language model with information about the connector builder. It doesn't know about it because it's a relatively new product, and there's the knowledge cutoff for the language models. But as Roy explained, we don't need to retrain anything here because we can just inject the relevant pieces of information at runtime, at question answering time, basically. And I will show how this looks like. So first step is to move the data from GitHub to Pinecone. And we can do this in the Airbyte UI. You can either run this locally or just sign up for a trial on cloud.airbyte.com. And we just create a connection from here. All right, so the source is GitHub. So I'm selecting GitHub on this list. And now I need to configure it. GitHub is really easy to configure because I can use OAuth to authenticate. In my case, this is just authenticating right away because I clicked approve before, and it remembers that. In your case, it will probably say something like you need to allow Airbyte, the Airbyte application, to read on your behalf. Now we need to configure the GitHub repositories we want to sync. In this case, we want to sync the Airbyte HQ Airbyte repository, which contains, which has a lot of issues about the connector builder, which we want to teach our LLM about. And then there's a few optional fields we can fill out as well. In this case, I will just fill in the start date. So to make this demo finish quickly, I will just sync issues that got changed today or late than that. So from midnight today. In a real world case, we would go through all the issues, but this sync will take a while because there's a lot of issues in the Airbyte repository. All right. Now I'm hitting setup source, which will check whether my configuration makes sense. So whether the authentication settings whether my authentication with OAuth is actually successful, whether the repository exists, all of these things. This worked fine. So the test is passed and I have a source now. Next part, I need to set up a destination. So we want to move the data to Pinecone. So I'm selecting the Pinecone destination in here. And in here, I need to configure a few more things because, as I mentioned, the Pinecone destination is not just doing the loading into the destination database. It is processing and embedding and then eventually indexing. So let's start with the processing. As I mentioned, data is coming in as records in the Airbyte in Airbyte speak, which means individual units of data, which are just JSON objects. So in this case, each JSON object will be one issue, and it will have a bunch of fields for all the things, all the properties a GitHub issue can have. And now we need to configure how to turn them into individual documents that can be retrieved when a question needs to be answered. The first thing to configure here is the chunk size, which is the amount of tokens, which correspond roughly to a syllable or a short word, that are treated as individual documents. There's no right or wrong number here. You really need to test with your kind of data to see what's right in that sense. If you put in a large number here, like 1,000, then it's maybe a little bit more than a page of content at once. So it's a relatively large context. Maybe in your case, questions don't require that much information, and the language model could not find the right chunk because of that, because the search is not precise enough. But if you go too small, then maybe there's not enough context around the thing you're actually interested in, so the language model can't make sense out of the document. So this is something that can be tuned for that specific use case. Then there's to configure which fields from my record are metadata, so things we want to filter on later on, and which fields are text fields which actually should be embedded, so we can do the vector similarity search on it. When we don't fill in anything as metadata, then it will just use all the fields as metadata, which is what I will go with for now. And for the text fields, we are going with the title and the body field, because for GitHub issues, these are the most important ones that contain the relevant bit, which should help a lot to find the issues that currently matter for the user. All right, so there, as you can see, there's a few other settings around processing, because just the chunk size is a very simplistic way of splitting up large documents. And you can go a bit further than that by configuring which separators to prefer, to find nice places to cut up one document, so it's not finishing in the middle of a word or something like this, but it's always using paragraphs or something like that. There's sensible defaults, of course, but you might want to tweak this for your specific kind of data. The embedding is relatively straightforward, because we just call to OpenAI here, pass the text chunks generated by the processing, and then receive back our embedding vectors. what we need to configure here is just the API key. So let's just copy that one in. And now the most important part is where to actually put these metadata plus text chunks plus embedding vectors. To do that, we need to create an index in Pinecone. So I will hop over to the Pinecone console where I can do exactly that. We create a new index here, webinar test. Next thing to configure is the dimensions, which is the number of items in these embedding vectors. So how many numbers there are produced in how much dimensions our vector space has. This depends on the embedding mode I'm using. So in this case, I'm using the OpenAI embedding, and scrolling down here, I can learn that OpenAI is for the text, for the model that we're using here, using 1,536 dimensions. So we need to make sure this number matches up. And then I can configure the scale of my index. I will just go with the small one because this is just a basic demo. And now I can create that index, which will initialize and be up for usage really quickly. All right, now I need to copy over a few settings. There's the environment I need to set. There's, of course, the name of the index, which is webinar test. And then there's the API key for my Pinecone installation, which I can get from the API keys page. Just copy that one over as well and fill it in here. And then I can, from here, set up the destination very similar to the source. This is now checking whether all of these things are consistent with each other and whether they are correct. So whether this OpenAI API key works, whether this Pinecone API key works. And if everything's fine, then we can, in the next step, set up the actual connection between the two. Because right now we only have the source configured and the destination configured. There's actually a few things we need to set on the connection level as well. So when we're moving data from that source to that destination, how does it actually look like? The things we can set here are, for example, the frequency, how often we want to move our data over. So should it happen once a day or every hour or just manually? This is relevant because, obviously a shorter frequency means that your data will not be as stale for your users. So we'll always know about the latest and greatest things. But of course, it's more expensive to run these things more often. So in this case, we will go for manual. So you need to manually trigger the sync from the Airbyte UI. The most important part, though, is actually the streams we want to sync, because the GitHub source is not just offering issues, it's offering, as you can see, lots of stuff. You can sync users, you can sync tags, and all of these things, which we're not interested in for this demo. So I will disable everything except for the issue stream. This one I want to copy over. By clicking on it, I can also drill one level deeper, and for that stream, configure which fields I'm actually interested in. Maybe assignee is not interesting to me, so I can just disable it and it will not be synced. Same for milestone and so on. But this is all the fields that will end up in our destination as metadata fields, except for the title and the body, which will, because we configured that in the destination, be summarized to a text, to the text of that record, and then be chunked up and embedded using the OpenAPI. All right, so we don't need to configure too much for this demo here. I'm going to set up the connection, which will save this connection from GitHub to Pinecone to my Airbyte instance. And now I can trigger a sync using that sync now button. If you configure a frequency, then this will start to run right away and will always keep up with the schedule. So now the sync is running. In the job history tab, you can also see what's going on by clicking the view logs button. So this is where you can see what's actually going to happen. So you don't see the actual data here, but you can see eventual problems or when something doesn't work right. Okay, this is going to take a minute or so. So let's hop over to the actual application we are going to build. So Roy explained how RAG works in general, retrieval augmented generation. What we're doing is we let the user input a question. What do they want to know? then we embed this question using the same embedding model we are using for our documents, our truth data, OpenAI. And then we are using this embedding of the question to find similar vectors in our database, because similar means they are related in terms of their meaning. So if a question is related to an answer, then this is probably a relevant piece of context. So this is what we can use to answer the question of the user. So we retrieve the question from the user, we embed the question from the user using OpenAI. Then we are going to do a search against Pinecone with this embedding vector. We retrieve back the best fitting documents related to that question. And then we are passing these along with the question to the language model and have it produce a coherent answer based on what the user wants to know and the relevant pieces of information. And this is how that looks like in code. As you can see, it's very simple to set up, mostly because I'm using the LangChain library here, which offers nice convenience wrappers around all the pieces I just talked about. The general flow of embedding the question, getting the fitting documents, and then checking them into the prompt, and then having the language model answer on that is called retrieval QA, retrieval question answering chain in LangChain. So we can just import that one. Then for the embeddings, as mentioned, we're using OpenAI embeddings. As the language model, we also use OpenAI ChatGPT model. Could use something else here, but it's just handy because we can use the same API key. And then for the vector store, we use Pinecone, obviously. So we just need to import all of these. And the next step is to initialize all of these. So you can see we just initialized embeddings wrapper. We initialized Pinecone based on environment variables for the key, the environment, and the index. So this is super similar to what we had to do in Airbyte, because it's basically connecting to the same database from the other side. The job running here is loading the data in, and this is where we are actually using the data, plugging the data out when we need it for answering some question. So this is putting everything together. We built the retrieval QA chain with the OpenAI language model, and with the vector store as a retriever. And then we have this very simple print eval loop, which queries the user to input a question. Then we run that chain, get back the answer, print the answer, and then start over again. So that's how it works in general. Switching back to the UI, we can see now that the sync succeeded. So it went through 116 records. Each record is one issue. In this case, these are the issues that got changed today. So this is all the things that happened today in our in our sync. Hopping over to the Pinecone console and checking out that index, we should be able to see these issues as well, right? So scrolling through here, we can see there's now 154 vectors stored in our index. This is a little more than the records because some of them got split up because they went above the limit of 1,000 tokens, and there's now multiple vectors in Pinecone for one record. But if you look at all the fields we have stored as metadata, you can see how this works under the hood. There's the text that got embedded, the vector we got back from OpenAI for this text, and then there's all the metadata fields. For example, there's the number, which is the actual issue number. There's a draft state, whether this is a draft or not, whether it's locked or not. As you can see, all the fields we did not unselect got synced over. And then there's also these _AB fields, which are important because they're tracking the record ID and the stream this came from. So we can update this after the fact when things are changing. All right. So we do have the data in the index. We do have our application. So now we can put the two things together and actually answer a question. To do this, we need to just get the API key again. And as this is a simple terminal application, I can just go ahead and load the Pinecone key real quick and start the Python script. This is now connecting to OpenAI and Pinecone. Everything works, so it prompts me with the question, hello, I'm the connector development bot, how can I help you? And I prepared a specific question here. I really hope this works now. So something you can do is to have a format for the date that is returned from APIs when using the connector builder. And sometimes this date needs to be different for request and response. So can you specify that? And if yes, how can you do it? We'll send this question. And as you can see, it does not work. Let me just try to set that where maybe I did something wrong here. All right, seems like something doesn't work correctly. Maybe the key is not set properly. Okay, so this does not seem to work properly. Let me just try one more time real quick. All right, so I'm not exactly sure what the problem seems to be here, but yeah, it seems like something is not set up completely right. So what I wanted to show here, which unfortunately doesn't work correctly, is that we have this question, and the answer, the question gets embedded and sent to the query, and it will retrieve a matching document from our Pinecone vector store, even if the wording of the question does not match what how the issue is phrased itself. So when looking at the issue itself, this is the issue I was trying to work with. Then this is saying incremental sync with different format incoming outgoing. And even though if I'm sending this question using a question like can I have a special format for timestamps in the request and the response? Like I'm saying special and timestamps instead of different and format, different and date and so on. This doesn't matter, because what the vector representation is doing here is that it's embedding the meaning of this issue and not the individual, like not the keywords or something, and which is how a classical search would work. All right, so we can also look at this specific case, because oh, wait a second, I think I just realized my issue. I called this webinar test, but in here I called it webinar index. So let me try that real quick, whether it works. Yeah, that looks better. So yeah, as you can see here, it's now answering the question based on what I put in there. But as you can see, it's just saying, yes, you can do this, but there's not many details. And that is exactly what Roy mentioned with the prompt engineering and getting the prompt right, because we never specified here what the context of the thing we're actually doing is. So we just basically very bare bone passing the content of this issue to the LLM. So what we can do to improve that is to use a custom prompt. So it's very easy in LangChain to configure these things. So instead of using the default prompt, which is just like, please answer this question based on the context, we can give the language model context of what it's actually doing here. So we can say something like, you're a question answering bot operating on GitHub issues. Use the following pieces of context to answer the question. State where you got this information from. Include sample code if possible, just to provide a little bit better, like suitable answer for the thing we're currently dealing with. This is one thing we can do. The other thing is this contextual retriever here, which is an extension of the base vector store retriever, which we used in the previous example. And what we're doing here is to check whether we're dealing with GitHub issues based on that AB stream. And if that's the case, then we add the content the content itself, the text that we found using the similarity search, and also some meta information like the issue number or the current state of that issue. So running this extended prompt and asking the very same question, you should see a little bit of a more fine-tuned answer. So as you can see, it's thinking harder now, which is actually a thing because now the answer that's generated will probably be a little bit longer than the last time. But it's still the same thing that's happening behind the scenes. It's just going through the, it's just adding a bit more contextual information now to the normal, the basic prompt. So the flow is the same, but as we can see here now, it added more information. It included a sample code, which is also presented in the issue, and it also specified that this is coming from the GitHub issue 27153, which is the one we were looking at here. Right, so as you can see, this is something where if you want to get it, make it great, you need to invest some time to fine tune all of these individual components for your specific use case. But you can do this on the application side using LangChain, maybe even querying different databases and to get together the right context to answer the question to be helpful to the user. And on the Pinecone / Airbyte side, you can index much more data from different sources, and you always have that those metadata fields to pick the right pieces. So something I wanted to show here real quick, just to drive home the point, is like if the source, like this issue, is wrong and gets edited, for example, maybe it's not cursor granularity, it's just granularity, then when we update this, the LLM doesn't know about it because the source of truth for the language model is Pinecone. But to do this, to get this, the knowledge base updated, we can just simply trigger another sync or wait for an hour for the scheduled sync to kick in. And this will now move over all the changed issues. For example, that one, delete the old state in the destination and replace it with the new one, running the full pipeline as we've seen it before, because, and that's the part that's important part of the source, it doesn't only have a configuration, it also has a connection state which describes where to pick up, right? So what got synced already and what we need to sync from here on. In this case, this is just the updated add timestamp of the individual issues, which needs to be transferred over. All right, so while this sync is running, I'm going to go one step further and talk about how this would look like if we want to do a bit more things between the source and the original source, the GitHub issues, and the destination, in this case, Pinecone. So sometimes maybe it's relevant to get information together before we can do a similarity search in the vector database. So we need to maybe join sources together and having to produce relevant documents we want to present to the language model. And the way to do this with Airbyte is to first extract and load all the different data we are interested in through different Airbyte connections into a warehouse. And then we can use the different means of transformations, for example, DBT, to bring the data into the shape we actually need it for the language model, and then use a secondary Airbyte connection, which is sourcing from the warehouse and loading this into the vector database. So this flow wouldn't happen anymore just between GitHub and Pinecone. There would be a place in between where you can stage your data, basically, which will also speed up your process a lot, because especially API data sources can get relatively slow. And then you can do transformations and also run experiments from here, because you only need to load the data from sources once into the warehouse and can then run multiple run multiple versions of transformations, for example, and then load into the vector database very quickly to test out what things work and what things don't. So now we can see the second sync succeeded. This only moved 8 records because since I started this talk, 8 issues got changed, including the one I changed. And when asking the same question now again, it should pick up this updated example. So now, without any retraining and with something that just took a few seconds, and now our language model knows that the field is called granularity instead of cursor granularity now. So this shows how easy it is to keep your knowledge base up to date, but still have the full chat application running. All right, that's it for the demo. Thank you for sticking with me here through this little typo problem. And if there's any questions, I'm happy to answer. It's just checking the questions list here. Is there anything?
We had some great questions. I'll summarize some of what people were asking. Joe, great job, and thanks. It's not a real demo if everything goes smoothly. So we proved this is live and real today. Just a few questions were asked. One was whether we can work with custom embedding generation endpoints. Specifically, Cloudflare was brought up. In the questions tab, I mentioned that we do also support OpenAI compatible endpoints, which this one is, as well as Azure and several others. So if you want to use a different embeddings endpoint, many of them are compatible with OpenAI. And I see that, Joe's got it up on screen right now. So you can use those options. Another person asked if you can use database data with this flow. And yes, any of the Airbyte sources that has text data, you can use this flow. And our destination allows you to pick which fields are text and which should be treated as metadata. A couple more things. Joe, jump in if there's anything you want to add. But a couple more things I want to call out. We at Airbyte are treating text as data, and you can see that in our investments in destinations like Pinecone and investments in AI and LLM, such as we've demonstrated here. Soon coming is support for text documents in file stores such as S3, Google Docs, and other locations where you might have raw text documents. And those, in addition to things like HubSpot, Salesforce, et cetera, which are already on our sources list. More coming, and I hope you all stay tuned. Joe or Rowie, did you want to add anything I missed?
Not from my side.
I just wanted to say that this was a great demo. Kudos, Joe.
Yeah, and thanks everybody for being here. And provide us feedback, create issues, find us in Slack, and let us know what you think as you try this out. And look forward to hearing your feedback and the great things that you build with this platform. All right, have a great day.
Bye, everyone.